Alright, the next section that we're going to deal with, as you can see, is electric power. Electric power is the same as mechanical power that we learned way back when in the last semester. Power was defined as work over time. It's the same kind of thing here. It's just now we have to change the work over to an electrical version of it, which we've dealt with in this chapter and in the last chapter. So let's take a look at that. We know that power is work over time, and we rewrite that work then, and we multiply both sides by t. Work is equal to power times time. All right, and so we also know that a volt is a joule per coulomb. That means voltage is equal to work, which is joules, over coulomb, which is charge. And if I rewrote that in terms of work, so that I multiply by Q, I'm going to get the Q times V equals work. Put those together as the transitive properties, set them equal to each other, so QV equals PT. Now I divide by T to get power by itself, and I have this equation P equals QV over T. But, and there's always that big but, Q over T, Q is coulombs, T is SI unit is seconds. Coulombs per second is what we define as current, which is I. So I can replace the QT with I. And that means that power can be calculated by taking the current times the voltage. Now, one more wrinkle in that. According to Ohm's law, voltage is I times R. And so I can take I times R and replace the V with that, and I get this little expression, so I times I is I squared times R. And the beauty of these two equations is you don't have to have exclusively all the parts of Ohm's law to figure out what the power is. You can use the equation, one equation with the voltage and one equation with the resistance. Okay? It's just that it's a little bit different in the current when we do that. So let's take a look at the examples I gave in the script. I have a 250 amp current going through a resistor of 16 ohms. So that's my I and that's my R. So the question is, what is the power? Well, the power is defined as let's see, I got I and R, so this is going to be I squared R. So I have I squared, well, I need to change this to amps, so that becomes 0.250 squared times the 16 ohms. Oh, I should put the label, that's bad, I have to get into. Amps times the 16 ohms, and according to the equation I have over here, this is going to be I squared R. I just realized I did the calculation wrong over here, so I'm kind of a little bit struggling here. So that should be I squared R like I had, and so that should be equal to 1 watt. Okay? Alright. Now, the next thing I want to talk about deals with energy. Alright, here we go. And so for energy, what's going on there is that we now have, again, power equals work over time. But again, work is energy, which is heat. But now I'm going to focus on the E part of this. So I'm going to change that to P equals E over T. Why am I doing that? Because what we're going to look at is the energy aspect of the power. When you get, well not you, but when your parents get charged for electrical bills, it's going to be expressed in this fashion here. Now, if I get E by itself, multiply both sides by T, I get E equals P times T. So, the power company charges according to the energy cost using this formula here, but the power is not in watts, the power for that is kilowatts. And the time is not seconds, it's hours. So they charge in terms of kilowatt hours, and the meters that your house has is measured in kilowatt hours. And so they charge a certain amount. And it varies from power station to power station or company as to how much they charge and where you live and all that stuff. If you ever take a look at your power bill, you might be able to see what they charge specifically. I use nice rounded off pennies. They go like 5 or 6 decimal places. Whatever. Your energy then is the kilowatts hour comes from this formula right there. So let's take a look at an example of that. You have a refrigerator running for 1 week straight, hopefully longer than that, but let's just take a 1 week period in which the refrigerator runs. You go to page 610 to get the power rating for that. If you look at it, you'll note that it is 500 watts for a frost-free refrigerator, which means it automatically defrosts the freezer part of your refrigerator. The cost is 12 cents per kilowatt hour, which we express in terms of dollars is $0.12 per kilowatt hour. The question is, what is the total cost? And since we're using the formula E equals PT, and that equals the kilowatts times hours, so we have to figure out how many kilowatts and how many hours you're dealing with here. So let's do the kilowatts first. We know that it's 500 watts. And we're going to multiply that by the number of hours, which is 1 week, which is 7 days, times 24 hours per day. And then we're going to change the watts to kilowatts. So we'll put 1 kilowatt on top and 1,000 watts on the bottom. Multiply all that nonsense through, and you get, looks like you get 84.0 kilowatt hours. Now, we're going to multiply that by the rate, which is 12 cents per kilowatt hour. And your cost now becomes $10.08. So you have this refrigerator, and that cost, 12 cents seems to be right around the normal one. I don't know what Fort Myron pays. We pay about 11 cents for ours. But that means your refrigerator is costing $40 a month to run. And that's a fair chunk of change. But that's how they calculate it. So, your practice problems. These 5 problems here at the end. Remember, page 610 is where you get the values for the power rating for each of those appliances they talk about. Have fun.